Okay, we are in the second unit right now and we're looking at forces, and what we're going to study today is extremely important when it comes to forces. It's Newton's laws. Now, often when we study physics, there are certain things that are so important to keep straight that you can't make sense of things moving forward without this. These are Newton's three laws involving forces. Newton's first law is what's called inertia. So I always like to write down small descriptors or single words that summarize what the law is. And basically this law says that things in motion tend to stay in motion and things at rest tend to stay at rest. Let's try and think of a few examples. If you were sitting on top of the car and the car started moving, you would stay on top of that car due to friction. If that car started going 100 kilometers an hour and quickly veered to the right, there wouldn't be enough friction to hold in place. You would keep going straight. This is inertia. You had velocity or acceleration going in that forward direction. So once the car turned out from under you, if you were sitting on top of that car, you would keep going straight due to inertia. Things in motion tend to stay in motion unless an outside force acts on them. Another example of inertia with cars. If you're driving along in a car and you slam on the brakes, the car stops, but you're not attached to the car. Since you're moving forward, you will continue to move forward right into the steering wheel. Now let's look at the second half of that. Things at rest tend to stay at rest. If you took a tablecloth and you took out a wine glass, you put the wine glass on the tablecloth and you pulled the tablecloth very quickly. That wine glass would stay still and the tablecloth would move. There wouldn't be enough friction to pull the wine glass along with it. Things at rest tend to stay at rest. That wine glass wants to stay at rest. Folks, I highly encourage you to watch 2 or 3 videos today on Newton's three laws. The first one is inertia. Now, the second law is the one that they cover the most in the content from today. And that second law is just a formula. The net force, because remember, there's more than one force, or can be more than one force acting on an object. Gravity, normal force, applied force, friction. If there is a net force, we will get acceleration, and that will be that will be dependent on what the mass of the object is. The lighter the object, the greater the acceleration. So this is often rearranged to look for acceleration. Remember, it's important. The only time we get acceleration is when we have unbalanced forces. So for example, if a brick is just sitting there, there's gravity on it and there's normal force on it, they cancel out. That brick is not going to move. Now if we put an applied force on it, which is greater than the force of friction, we will get movement occurring. At the end, I'm going to do a trickier type of problem just to show you one pitfall. But what you're going to find is at the very beginning of this session, they're going to talk a lot about Newton's second law, force equals mass times acceleration, and they're going to focus on that. The third law is one that people sometimes overlook, and it's so very important. All forces come in pairs and involve 2 or more objects. Let's take a look at a couple of examples of this. We have the force of gravity acting on this brick, pulling it down. We also have a normal force exerted by the surface here pushing back. If we have a rope with tension on it, maybe somebody's grabbing onto that rope and pulling it, there is a force exerted in this direction by the object doing the pulling, but there's also a force in this direction that's exerted by whatever is being pulled. Remember that forces always come in pairs and it's one object acting on the other. Let's take a look at an example where the forces aren't always going in exactly the same direction. So let's take a look at what I have here. I have a 10 kilogram, so that says 10 kilogram brick sitting on a flat surface. So let's do the force of gravity. it's equal to mass times acceleration. So that's 10 times the acceleration due to gravity is 9.8. That's negative 98 newtons. Remember, the negative is a direction there. It's also saying we've got a force of friction of 2 newtons, and we've got a force from somebody. So if we drew a person here, and that person is pulling on this rope with 10 newtons of force, what we'll notice here is this is a y direction force, this is an x direction force. We're going to have to split this up into x and y using SOHCAHTOA. So we're going to have to take the cos of the 45 degrees and times it by the 10, and this will get 7.07 newtons in the y direction, and then we'll have 7.07 newtons in the x direction. Okay, once again, I took the cos of 45, and I took the sine of 45 and times it by that 10. Okay, it just so happens that the cosine sine of 45 degrees is 0.707. Note this, we have 7.07 newtons pulling in this direction, 2 newtons of friction in this direction. The difference between the two is 5.02 newtons east. So if we ask the question, do we have acceleration? Sure we do. We have an unbalanced force. We have 502 newtons east. We could also say we have 5.02 newtons in the positive direction of excess force. Acceleration equals force over mass equals 5.2n, which equals about 0.5 meters per second squared of acceleration. Okay, so I find out my unbalanced force in the x direction, and then I divide that by the mass of the object, and this will give me the acceleration. Here's another interesting thing. If we have negative 98 newtons going in this direction, what is my normal force? Well, you would think it would be 98 newtons, but my forces going up equal my forces going down. So if I have 98 newtons going down and I have 7 newtons going up, I'm left with about 91 newtons for my normal force, because these forces are balanced. Sorry, this force plus this force is balanced with this force. How do we know that? Because that brick is neither moving up or down. If it's not moving, all of the forces going up must equal all of the forces going down. The reason we have acceleration in the x direction is because the forces in the x direction, in a positive x direction, are greater than those forces in the negative x direction.